Okay, when you graph velocity against time, you show the acceleration as the slope of the line. And you know this, we talked about this. This is just kind of re-hitting it because it is important. You've got these notes. If you don't want to write it down, you don't have to. So if we look at this, can you reliably identify the intervals for which acceleration is positive? Yeah. So go ahead and jot them down, and I'll do them up here. It's the only ones I see. Do you see anything else? I think that's it. So where would the acceleration be negative? Those? So I'd say these are positive, positive, negative, whoops, negative, negative. Okay, cool. Of course, because the minute's easy. And we did this. We walked through some of these, but let's just make sure. So on this one, where are the positive accelerations? Oops. Be color consistent. Positive. Positive? Okay. And in that first instance of positive acceleration, is it speeding up or slowing down? Speeding up. In the second instance of positive acceleration, is it speeding up or slowing down? Slowing down. Okay, good. I just wanted to review. So now we'll talk a little bit more about constant acceleration. Note that we have only looked at things that have constant rates of acceleration, or we've looked at average rates of acceleration. In the context of the physics we're going to do, we're not equipped to talk about changing rates of acceleration very well. Those would be curved lines for acceleration time graphs, and we really can't do much of that. Based on the idea that we have constant acceleration, or we can at least average out acceleration to get a constant value, we can use the two equations that we have, and we can sort of extract from that four basic equations for kinematics. And kinematics is just the study of motion, so we're talking about displacement, velocity, time, all that stuff. So we'll start with the first derivation. How many of you absolutely love doing algebraic derivations and it makes you happy? Okay, they're fun. Algebra's recreational. I love it. Would we agree that it's true that average acceleration is equal to the displacement over the change in time? Yeah? Okay, wunderbar. Now, if, in fact, the rate of acceleration is constant, is there another way to average two numbers? So if I give you 4 and 8, can you get me an average? Add them up, divide by 2. So it's also true that V average equals the initial velocity plus the final velocity divided by 2. You would agree? Wunderbar. This is just a series of logical statements with which you will agree. You agree, okay. So, therefore, and this is the mathematical sign for therefore, little 3 dots. Do you guys use that in math? No? I think it's a geometry proof thing. I don't know. So because VA is equal to this and also equal to this, we can then say, dun, da, 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 let me shrink this. We can also say that it is true that delta x over delta t equals VI plus VF over 2. So what we can then rearrange to do, the standard form of this I'll give you, we could rearrange this to solve for any of the factors in there. The standard form that you'll put on your note card, we typically do this. So delta x over delta t then equals 1/2 VI plus 1/2 VF, or 1/2 VI plus VF equals delta x over delta t. Let me shrink this again. Therefore, delta x equals 1/2 vi plus vf over delta t. So that's the standard form that we usually use on the note card. What this allows us to do is find displacement or time when we don't necessarily know the average velocity, but we know the initial velocity and the final velocity, or we can find initial velocity or final from the displacement and the time. So let's do a 2C practice problem. So they reference these problems as displacement with uniform acceleration. For these problems, we do have to assume that the acceleration is uniform. And so we're told that a racing car reaches a speed of 42 meters per second and then begins a uniform negative acceleration using the parachute and braking systems, comes to a stop 3.5 seconds later. How far does the car move while stopping? So, of course, we are going to list our variables, VF, VI, delta T, and delta X. And what are we looking for? Delta X. So we have a time of 3.5 seconds. What's our VI? I'm working from the bottom. Yeah, it's the 42 meters per second. And our VF is?
It's 5.5 seconds per time.
Oh, it's 5.5? Yeah, it is. Humph. I should get my reading glasses out. Okay. 5.5 seconds per time, sorry. So what's the final? 0. Zip, zilch, nada. So obviously we're going to use the equation that we've got because it's the one that ties together those four things. Pretty soon you're going to have four different equations, and you're not going to know which one to use. They're all going to be mixed together. So that's why I want you to get in the habit of recording your variables first, because the key to which equation do I use is which equation ties together the things that you have and the thing that you need. So, of course, for us right now, we only have this. Delta x equals 1/2 vi plus vf times delta t. So it's already arranged. We don't have to do a thing. And this one's very straightforward. 1/2 42 meters per second plus 0 meters per second times 5.5 seconds. Let's do a quick bit of dimensional analysis. Meters per second plus meters per second equals meters per second times seconds. Hey, that ends us up in meters. That's good because that's where we would like to be. Okay, we get a raw answer of 115.5. Did I just put seconds there? Let's try meters. How many sig figs do we have? 2. So what's our sig fig answer? 120 meters or 1.2 times 10 to the second meters. Either one is acceptable. We don't have to use scientific notation. Generally, as a rule of thumb, I always say that if you're over 1,000, you should probably be in scientific notation. If you're under 1,000, you don't really need to be. We can manage numbers with, under 1,000 and over 1,000th. Once we get outside that 10 to the third range, we probably should be in scientific notation. Okay, questions on this. All the book problems are assigned for this. So that is page, I don't know what page. That's page 53. But before I cut, and I would also, if you've got your note card out, put this on your note card. So what if we want to know displacement? In the last one we had a final velocity. What if we don't have a final velocity? What if we don't have a way to get a final velocity? So if we know the initial velocity and the time and the rate of acceleration, we can get to displacement without ever knowing how fast the thing was going at the end. So, would you agree with that statement? Average acceleration is the change in velocity over the change in time. Of course you would, because you're all reasonable people. Okay, would you further agree that delta V is nothing more than VF minus VI? Okay, good. We're all reasonable people here. So then, because this is equal to this, we can say that average acceleration is equal to VF minus VI over delta T. But this doesn't solve our problem of not knowing VF. There's a trick we're going to use a lot in physics, which is rearranging an equation to solve for the thing we don't have to create an expression for that thing, and then jamming that expression into another equation to bypass the thing we don't have. Doesn't that sound like fun? Yes, I think so. All right, so since we know that we're not going to have VF, we're going to solve for VF. Okay, so, whoa, where did that come from? I don't want that. All right, so I'm going to solve for VF. To do that, I'm going to do A delta T equals VF minus VI. Well, then A delta T plus VI equals VF. This is often written as VI plus A delta T equals VF. This is a nice one. Actually, you probably should put this on your note card too, even though it's not explicitly walled off. I always like this one because it's one of the kinematics equations that you can look at and think logically about and realize that, oh, well, how fast you end up going is equal to how fast you started off going plus how long you accelerated. Oh, it's just logic. So it's actually an easy one to remember. Okay, so we've got that. We're going to use this. I'm going to copy this. I'm actually going to go to the next slide with it. With that expression for VF, and in the first slide, we derived this. Delta X equals 1/2 VI plus VF whole mess times delta T. Well, guess what? I have VF here. I have an expression for VF there. It's only going to be ugly for a second, folks. It'll get better. So we're going to jam that in there sideways. Delta X equals 1/2. And I'm going to use brackets and parentheses to clarify. VI plus the quantity, VI plus A delta T, close parentheses, close brackets, all times delta T. Ooh, well, that's exciting. Excellent. Love it. So what do we get here? Okay, well, let's go to the next step. Delta X equals 1/2. Well, VI plus VI, this is all addition in here, so we can just vaporize, whoops, we can just vaporize the parentheses. So VI plus VI gives us 2 VI plus A delta T times delta T. So now we just have to distribute. This is the easy part. So delta X equals, well, 1/2, and I'm going to do one thing here which simplifies things somewhat, I think. Let's move this here. Let's move that there. I'm going to put all the things that we're distributing at the front of the bracket because I think that makes a little more logical sense. So we have 1/2 times delta T times 2 VI plus 1/2 delta T times A delta T. So now we're just down to combining like terms and doing a little bit of multiplication. So delta X equals, well, 1/2 times 2, that cancels itself out. So we have, and this is generally written, this is one of those things that there's no solid reason for, and yet I cannot bring myself to write it any other way. VI delta T plus, well, the 1/2 isn't going anywhere. A doesn't have any, we can't do anything with that, but delta T times delta T is, of course, delta T squared. So this is the next of your kinematics equations. This is number 3 of the golden equations. Delta x equals vi delta t plus 1/2 a delta t squared. It's pretty. Now I'm going to point out a couple things about it. We can use this when we want to know delta x. We can use it when we want to know vi. We can use it when we want to know acceleration. There's a limitation on it when we don't know delta t. What is that limitation? And then I'll tell you about my peculiar algebra allergy. What do you notice about the delta t in there? If we have vi and we want to use this requires use of the quadratic equation. It can be done. It's not that hard. One year, a really clever cookie in physics, after we had done a whole bunch of algebraic bending and twisting and manipulation to work around using the quadratic equation, she came up and she liked the quadratic, so she had just used the quadratic, and she said, hey, did you notice how close all the substitutions you did got us to the quadratic equation? Yeah, it does. If you're comfortable with quadratic, the hardest part is getting stuff into form to use it usually in physics, in an actual situation, not in an abstract math situation. But you can. If vi is 0, do you have to use the quadratic to find time for this? Nope. Because if vi is 0, that first delta t disappears. And it's nice because in a lot of these, we have situations where, well, if vi is 0, a factor will disappear. Obviously, same for vf and anything that it appears in. So, all right, let's do 2D. Okay, plane starts at rest at one end of a runway, undergoes uniform acceleration of 4.8 meters per second for 15 seconds before takeoff. What is its speed at takeoff, and how long a runway does this plane need to get off the ground? So 2 different questions, both of them using equations that we have recently derived. So for part 1, and we get lots of 2-part questions in physics. It's a good idea to somehow set those apart. I'll actually just call this question A. Okay, so for question A, we have VI, we have the rate of acceleration, we have the time, and we want to know its final velocity at takeoff. Again, when you list the variables that apply to a given part of the problem, then you're able to see which equation you should use. So you've got 2 equations to pick from. Of the 2 equations we just derived, which equation ties those 4 things together? Who would agree that VI plus A delta T equals VF nicely hits that, and that? Okay. Good. I'm so glad you agree. You're such agreeable people. So our VI is 0. Our rate of acceleration is 4.8 meters per second squared. We have a 15-second run, and we're curious about VF. We don't have to rearrange anything on this, which is totally bogus, but that's okay. So 0 meters per second plus quantity 4.8 meters per second squared times 15 seconds equals VF. What do we have? 72 meters per second. That's sig figged correctly because we have 2 sig figs, so we're good. That's pretty fast. All right, now let's look at the length of runway that's needed. So for part B, we still have a VI of 0. We are given delta T of 15 seconds, and we are looking for delta x. Oh, we have the rate of acceleration. I'm sorry. We have the rate of acceleration, 4.8 meters per second. You would think I had never per second squared. And we're looking for delta x. We're looking for the displacement that's required. So we'll set that aside. I feel as though we have an equation that will neatly tie these factors together. Delta x equals vi delta t plus 1/2 a delta t squared. Hey, that'll do it. This is nice because can we get rid of anything in that equation right off? Sure can. That goes away. Vi is 0, so that part disappears. I then generally rewrite delta x equals 1/2 a delta t squared. And to plug in, we're going to get 1/2 times 4.8 meters per second squared times 15 seconds squared. Dimensional analysis, we've got meters per second squared times seconds squared. Lo and behold, that gets us meters. We're looking at a displacement. That's convenient. Delta x equals 540 meters. So two things to be aware of. Most common mistake on this kind of problem, by far, is forgetting to square time. Forgetting to take the square of something or forgetting to take the square root of something is pretty common. Yes, sir? So, very commonly, these kind of questions are given as comparison questions for the physical world. And this is where you could actually use a Fermi in everyday life, in real life. We very often get a question like that, and we're told, the runway is 500 meters long. Can this plane successfully take off on this runway? What would the answer be? No, they're going to go right off the end. They got 40 meters that they still need to be accelerating to get off the ground. Ain't going to happen. And that's a very common type of problem here. In those situations, you want to be really careful not to put that 500 into your calculations. That's just what you're comparing to at the end. So the question was raised, hey, we already figured out final velocity. Couldn't we just use delta x equals 1/2 vi plus vf delta t? You could. Remember how I said there are 6 ways to solve it? How many times are you going to say that, Moser? For Pete's sakes, we heard you the first 30. There are 6 ways to solve any physics problems. 4 of them will get you an answer. 3 of them will get you a right answer, and 1 of them is elegant. Yeah. I make dumb mistakes a lot. Maybe none of you have this problem. I try very hard not to rely on things that I have calculated to plug into something else. Because you can cause a cascade of error. If you have an error in problem 1 and you're plugging in that value from problem 1 into problem 2 and then plugging in that value to problem 3, you can just sort of snowball. So what I do when I have the option to do so is I go back to the givens and I try to, as much as possible, stick to using an equation that allows me to tie the givens that I have to solving it. Now, there will be cases where you cannot do that. And that's where we look to other equations. And very often, and as we go further in chapters 2 and 3, we'll do a lot of substitutions where, and actually, we could, if you really wanted to have some fun with algebra, and I sense we're simpatico, you could go ahead and use that first equation, and if you just did the algebra and solve for delta x, you'd end up with that, which is pretty cool. Because we've just derived these from the same thing, so we're just saving ourselves the steps. But yeah, could you calculate VF and then plug it into the other equation? Yeah, you could. I don't like to do that because I like to stick with the givens I've got so that I don't do the cascade of error showdown. But okay, that is page 55, 4D, or I'm sorry, God, 4D, no. So 2C and 2D, page, 53 and 55, all assigned in the book. And I'll cut you loose to work and ask questions, and that's it. I'll have the worksheets for you tomorrow.